Good morning, good afternoon, good evening again. Michele Calvello from the University of Salerno and the International School on Landslide Risk Assessment and Mitigation. Welcome back. This is the second part of our lecture, my lecture on landslide early warning systems. So let's resume from where we left. I'm going now to go through a series of examples of operational systems in different areas of the world, territorial systems. I will concentrate my examples on territorial systems only. But by looking at those systems and the different components of those systems, how they are indeed working, we will somehow hopefully better understand what I said so far when I was trying to introduce all the different elements that are indeed important for landslide early warning systems. So let's start, and we will start from the last one of these examples, Rio de Janeiro. Here it is. We fly virtually, we go virtually in Brazil, and we are in Rio de Janeiro, the city. What is there? What do we have as systems there? We have indeed two different systems. I can say that we have a sort of two-tier system, but indeed it's two different systems, both working over a wide area. Why? Because the Alerta Rio system, officially created in 1996 by the Rio Foundation, is indeed working over the whole city, so covering the boundaries of the city. We will see how in a very short while. The other system that I will introduce afterwards is called A2C2, Sistema de Alerta e Alarme Comunitário para Chuvas Fortes. And we are dealing with some favelas, informal communities of the city of Rio de Janeiro. Some of the elements are shared with Alerta Rio. This system, the second one, A2C2, is designed not to be permanent, so it doesn't. It has a purpose, the purpose of warning within those communities in the areas where these warnings are needed for the time being, thinking that then maybe other actions, such as, for instance, structural mitigation actions or other actions, may take place to reduce the risk in those areas. Anyway, the city of Rio de Janeiro, we have many pluviometers installed throughout the city. Okay, here you see a satellite picture. You cannot understand very well the morphology, and but I can tell you that this is an area, forested area with slopes, and you can see that at the boundaries of this area there are many communities. There is indeed an important part of settlements, formal and informal settlements. And so anyway, let's not go into details of what Rio de Janeiro is. 33 pluviometers. Indeed, you can say that each pluviometer has an area of influence. So there are 33 areas that could be associated to pluviometers, so to measures of the rainfall. Yet, and here we go to, let's see if the pen is working. Let's have the pen back. We are thinking now at some warning criteria. What are the areas of the warning that we have? Sorry, the warning areas. Just a second. You would excuse me for a second. Here we are. The warning areas are 4. The zones of the alert are 4. So the entire city is, you can say it's divided in 33 areas that are areas of influence of the piezometers, and the rain gauges, the piezometers, will be the instruments that are essentially used to measure the rainfall that is falling, to measure with, to monitor the rainfall. Yet they are not alerting based on those areas. The zones of alerts, the warning areas, are only 4: Zona Sul, Chapai-Paguá, Baía de Guanabara, and Baía de Sepetiba. So you can see they have different sizes, but also because, as I said, maybe landslides do not happen homogeneously over the territory of the city of Rio de Janeiro, because they depend on where slopes are in it. I can say that the landslide alerts are indeed a component of Alerta Rio. Why? Because they also have rainfall alerts in 4 levels. So again, we are thinking about warning criteria. The 4 levels of the warning criteria are green, yellow, red, and black. If we refer to the landslides, the probability of landslides occurring based on measured rainfall, we refer to this part of the system. Somehow it's a little bit confusing, because you may have alerts and warnings that are of different colors if you think about rainfall, or if you think about the probability of having landslides associated to the rainfall. But anyway, we are concentrating on the probability of having landslides based on the rainfall measures. So let's not concentrate on the rainfall alert, but on the landslide. On the landslides, that is the probability of having landslides given rainfall conditions. You move from the nothing to yellow to red. Here it's what they call red, the third level, and then they call black, or at least they highlight with a black color, the 4th and most the highest level of alert. And you move from one to the other based on rainfall measures. I was already saying it. What types of rainfall measures? So what is a warning event? What are the thresholds that we associate to indicators of rainfall? The indicators of rainfall are the 1 hour intensity, the cumulative rainfall over the 24 hours, rolling cumulative rainfall, and the cumulative rainfall over 4 days, 96 hours. For each indicator, 1 hour intensity, cumulative 24, cumulative 96, you have thresholds. For instance, if you have more than 25 millimeters of rain in 1 hour, but not more than 50, you are in this yellow level according to this rainfall indicator 1 hour. But you may be in the yellow level, maybe also because maybe in 1 hour you don't get 25 millimeters of rain, but you get more than 85 millimeters over the day, up to 140. So basically, here there are some or statements. As long as one of these 3 indicators overcomes the threshold, you enter into those levels. If we think about the highest level, black, it's bigger than 80 millimeters per hour, or more than 220 millimeters, 220 millimeters per day, or even more than 300 millimeters over the 4 days, together with a 100 over 24 hours. So basically, one of these 3 criteria, one of these 3 indicators, as long as one of these 3 is overcomes the threshold, you enter in the corresponding warning level. Indeed, yellow, red, black. But if we want to say when is the alert really issued, the alert is when you go into the red. Then you have black on top of red, but as soon as you go into the red, there is the alert is issued. And how is it disseminated? So thinking about warning dissemination now, what we get here, the warning event, becomes an alert and goes to the civil protection, the municipal civil protection of Rio de Janeiro, and it becomes something that you have to send and SMS, maybe this picture, and also nowadays apps. This particular picture was taken a few years ago, so things are evolving as well. Okay, and an important issue here. There is this is a picture of a center of operations that the municipality of Rio de Janeiro created to manage emergency situations in the city. It's very important to have such a physical space, because in that space, when things when you start and you go from green to yellow and you start preparing for what can happen afterwards, and then you start disseminating, you start issuing alerts, you can have the media coming and finding in the same space the meteorologists as well as the geotechnical engineers of the office, geotechnical engineering office managing the alert system, as well as the fire department, the civil protection. So everything is, the centralization of the operations is a key component of a working operational system. Anyway, that was a side message from this slide. As an example, when I was there on the 17th of May 2013, and one day I checked on the web, you could see rainfall, yellow, basically everywhere in Rio de Janeiro. But for probabilities of landslides, you have the yellow and you have the green. So in these two areas, no problems for landslides, and the yellow and the other two. So the probability of landslides are different from the warnings for the probabilities of landslides are not necessarily the same as the ones for rainfall. And you can see that if we were looking at specific, so this is something that I got as an information, but that's not where the warnings are issued. No, if you're looking at a specific rain gauge, there is one rain gauge here. I guess it was on top of the Tijuca Massif in this case, where the red threshold has been overcome. Yet, if you go back, the yellow is the color of the general warning for both Zona Azul and Baía de Guanabara, okay, for those two areas. Let's move on to the other system. It's a different purpose, and therefore it's also set up very differently. We are addressing many favelas, many informal communities at the same time. They started from an analysis and a risk mapping of 107 communities, ending up with 103 communities as the ones needing an alert system because of some areas at risk. The alert system installed between 2011 and 2012. You have sirens, you have local rain gauges, you have gathering points for when it's written for when it rains a lot. And what else? I can tell you that in some of these systems there are also local pluviometers. In some others, in some of these communities, there are local pluviometers. Some other communities that are close maybe to other communities with a pluviometer, they don't have it. All of them have sirens located in strategic spots, because the siren has to then disseminate the information to the people living in the areas most at risk, the areas that were mapped as the areas at risk. What is the strategy of alert, alarm, how it is called? It's called alert and alarm procedure in English, of course, the translation from Portuguese. Rainfall, 1 hour, 24, 96, like for the system that we saw before, different thresholds though. So here it's a yes or no. It's not a yellow, red, and black. So a yes or no that is based on these thresholds that you see here, 40 millimeters of rain in 1 hour, or 125 in 24 hours, or 200. But anyway, those were what these are values that I'm reporting here that come from 2013, and they were evaluating at that stage whether they had to change them or not. Anyway, those thresholds you have to think about in each system. They are necessarily subject to refinements and to modification during the life of the system. Alert, as before, not as before, sorry, by means of a specific figure, specific role in the community. That is the role of people that are acting at the interface between the official authority, so the civil protection in this case of the municipality, and the community. So the people that are acting at the interface are these groups called NUDEC. Now I don't remember exactly the meaning in Portuguese of the acronym, what it means. But anyway, there are groups of people with some of them getting messages before the others. So before the alarm indeed goes on, so the siren, before the siren starts producing warning messages, in order to alert the population. The siren goes on if after some thresholds are overcome, also the managers take the decision to indeed switch on the siren. It's not an automatic process, but there is always a review by a group of people. Another important part of the early warning systems in general, but of this one in particular, because now we're talking about this one, is the dissemination of the information, what we call communication and education. So communication and education goes on with activities that include the production of posters, leaflets, calendars, cartoons for the youngest, but also with the simulated exercises of evacuation. When you, for a specific day, typically Sunday, you go and you simulate an evacuation, and in order to simulate the evacuation, there are techniques also to try to involve people that on that day, maybe it's a sunny day, they understand it's a simulation, they don't want to move. Simulations are in a way important. There would be a lot to say about participation, these sort of issues, but this is not the place to go on in detail on this. I can tell you that as an example, again, I'm taking as a reference the same day of the one that I did before. On that same day at 4 p.m., you could see in one of these communities, what was this one? The 24-hour threshold. Sorry, I cannot highlight this very well. Okay, was overcome. So red means supposedly you should issue an alert, but as I said before, there is a consultation between the meteorologists, the coordination of CO Rio, the civil defense, and in this case, by looking at also the forecasts for the following hours, they decided not to switch on the siren. And indeed, in this case, it was the good decision to take because nothing happened. So like it was a correct decision to take. Anyway, I move to another example, and I move to another example to highlight different issues. So let's move to Seattle. Let's move to the United States, the western part of the United States, where the issue that I want to address here now is the landslide model. Besides rainfall, there is something else that is taken into account. And as I said before, as a general comment, also in this case, there is the system is updated. So even the landslide model is updated. In 2000, the 3-day and 15-day precipitations were considered, then based on some analysis of data, in the area that they analyzed, then in 2004 there was an additional 2 components were considered, were included in the landslide model: the intensity duration threshold and the antecedent water index. So if we look here at the 3-day precipitation and the 15 days precipitations, there is a threshold, and this is one of the 3 criteria that is, so here I'm showing the database from which they derived the threshold. But I'm basically now here highlighting that there is a threshold, and this is one of the 3 criteria that is used in this model. The second one is the more classical intensity duration, where you have intensity, hourly intensity on the y-axis, and duration in hours, in this case, on the x-axis. And also here there is a threshold that is devised, highlighted, and then produced. And then there is something that is called antecedent water index. That is something that takes into account the situation of the soil before the rain gets there. That's also an important thing to consider. How are these 3 indicators, these 3 measures of rainfall and the humidity of the soil taken into account in the warning model? In the warning model, this is the procedure. So you basically move from, let's see, from the top, from what you have in terms also of, in terms of forecast for the different indicators. And if something is not overcome, you go to anything. If something is overcome, you go to a yellow. But then you move on, you observe, okay, snow is snow, but without snow, you observe the rainfall, and then again you check CT yes, CT no. If it's no, the CT less than you stay in green, you go to yellow, but you can move on checking the ED, and the ED together with sorry, the ED is afterwards. First of all, you go here, and then you go with ED and AWI, and depending on where they stand, you can go to orange or you can go to red. Basically, there is a procedure. So the warning model is using what you devised, setting up thresholds, and deciding what to do when. Here, as you see, the levels are 4: green, yellow, orange, and red. Most typically, that's the color code for the 4 levels. Black is an exception for the black that they use in Brazil, in Rio de Janeiro. And indeed, what was I saying? These 4 levels are also called with some names, null, outlook, watch, warning. So you can see names and also words are used differently in different places. Here, warning means alert, maximum alert. Watch means beware because something may happen. Outlook also beware, but at a lower level. Okay. In Italy, I would like in just 2 slides to highlight something, and we will refer to the regions Campania, that is the region where I come from, where I'm based, and Emilia-Romagna in the northern part. In Campania, what you don't see here is because it was in Italian, so I did it on purpose. In Campania, we have the classical, let's say, the most used subdivision in warning levels, 4 warning levels, a classical color code, green or yellow, orange, or red. When do you go to yellow, orange, or red? How do you get there? What is the warning model? Well, the warning model is based on the fact that each municipality has been classified based on risk scenarios, and some of them have the possibility of having shallow landslides, debris flows, because of their configuration of the terrain in the different municipalities. Once you are in those municipalities, so there is a list of municipalities, each one is associated to a specific rain gauge. Each rain gauge has been in operation for many, many years, some of them 80, 90 years. And so you have a statistical analysis of the rainfall data. And so you people have been defining thresholds based only on a statistical analysis of the rainfall data. Really not based on the correlation between rainfall and landslides, because there is not a good database of landslide occurrences, and so the authorities decided, let's use the rainfall. If the rainfall is exceptional, so return period more than 10 years, we have to issue an alert. If the rainfall is unusual, more than return period more than 5 years, we have to stay alert with a different level, or yellow if it's a strong rainfall, unusual, but we return a period of 2 years. But rainfall, what is rainfall? Cumulative rainfall, intensity of what? The idea is that in this area, because of the phenomena and the way of those phenomena develop typically on coarse grain material, so they react quickly to rain. So the important rain indicators to consider have been identified in 24 hours, 48 hours, 72 hours. So 1 day, 2 days, 3 days. So there are municipality by municipality thresholds defined for 1 day, 2 day, 3 day rainfall at the yellow level, at the orange level, at the red level. And with those in mind, once you record the rainfall, if you overcome a given threshold, you enter in yellow, orange, or red. That's how it works. If we go to Emilia-Romagna, the warning model again uses rainfall, but in a more, let's say, sophisticated way, also because they started their analysis of the rainfall with they use in the analysis of the rainfall also occurrences of landslides. So landslides that occurred in a wide, in more than 50 years with daily rainfall measures allow them to highlight deviations from the ordinary in terms of rainfall that cause the rainfall indicators that cause landslides. So they analyzed cumulative rainfall from 1 day all the way to 100 and plus days, and they set up a series of cumulative rainfall probability curves. They are called sigma curves just because, this is the 1 sigma curve and this one is 2 sigma, so deviations from the normal with 1 standard deviation, 2 standard deviations, and so forth. And so based on that, there is this procedure that tells you when you get more than 3 times higher than the normal for rainfall that are accumulated in the first 3 days. 3 days, as we said, also for Campania, 1, 2, 3 days, shallow landslides. You check also in this system the possibility of having reactivations of deep landslides, but in this case, the rainfall that is important is not the short-term rainfall, it's the long-term rainfall, even the seasonal rainfall. How do you account for that? You just go and you compute your rainfall with very long periods, from 4 days all the way to 245 days, almost 3 seasons. Okay, with that, again, green, yellow, orange, or red, according to where you are. Finally, let me close this brief illustration of case studies and places in the world by going to Hong Kong, where the first ever landslide early warning system was developed. As you can see, the city, similarly in some way to Rio de Janeiro, is hilly and a lot of developments alongside the hills. So there are situations that could be defined similar. In terms of the landslide model, long-term development, let's go all the way to the current version that was implemented in 2004. After experimenting with different indicators, 24 hours, 1 hour, at the end, it's the rolling 1 day rainfall that is the one that is most important for how landslides develop in this region, in Hong Kong, in this municipality. Watch out. What do they mean by landslides? Indeed, for them, landslides are not shallow landslides, debris flows, but landslides are slope instabilities in specific areas that are anthropic areas where people are. For instance, cut slopes or rock slopes or fill slopes, as well as they also include in that retaining walls. When you are constructing a retaining wall, all of them are clearly identifiable on the land. You know how many cut slopes, rock slopes, fill slopes. They indeed have IDs. They have positions in the city. So by analyzing what happened over many years to all of them in relation to the rainfall, at the end, it's the 24-hour rainfall, cumulated rainfall rolling, because you track it 15 minutes after 15 minutes. And you see that the higher it gets, this is a probability of failure with this indicator R24. The higher it gets, the higher the probability of failure. This is in log scale. And these, let's say, relationships, however, differ from one type of slopes to the other. Cut slopes, rock slopes, fill slopes, retaining walls. This is the landslide model that they adopt in their system. What's the warning model? Once you can compute those probability of failures, what you do is you count, you multiply those by the number of slopes that you have. As I said, every slope is identified, and there is a position where that is happening. They divided the territory in a series of 1 kilometer by 1 kilometer square cell. In each square cell, there will be a certain number of slopes. In each square cell, based on those relationships, you can compute F sub I. Therefore, you can compute this number. When you do this number for each square cell and you sum all of those numbers for the entire territory of Hong Kong, if you end up with this value, N24, that is bigger than, you just check this with respect to the number 15, at least that was in the version, the latest version of the model, then you have an alert. Otherwise, you don't have an alert. So this is the warning model. So this is how the alert is issued. How the alert is, it's a computation based on this scheme that I just highlighted for you. I can see in this slide that, I can show you in this slide that they checked at some point the performance of the system in relation to a period of 4 years, year 2001, 2005, and they could see that indeed, when they issued their alert, all the times that this number 15 is overcome, because this is N and this is number of landslides reported. So they issued 1, 2, 3, 4, 5, 6, 7, 8, 9 times the alert. 7 times out of 9, indeed, there were more than 15 landslides. So they did a good job, and then you can call this a true positive. So it means true positive. Couple of times they issued the alert, but it was a false positive, false alarm, because indeed the number of landslides were less than 15. And one time at the border here, but this is a good true negative, because neither the predicted nor the real number of events was higher than 15. Once you have this, you can indeed, it's basically, you can construct a contingency matrix and check what is your probability of detection or whatever, false alarm ratio, whatever you want to do, the miss rate, whatever you want to do. So they are saying at that point, they were saying at that point, we're doing a good job, we keep going. All right, I guess the 4 examples are over. So I put those slides for you there, and then I commented them because I wanted to show you real cases and talk about the different aspects sorry, of the let me just drink a little. Of the landslider running systems in operational settings. I close this presentation with a specific focus on model efficiency, performance evaluation. We are talking about the warning model. We are not talking about the warning system, not the entire warning system, but the warning model. How do we check whether it works, whether it doesn't work? The last slide. So in Hong Kong, they were checking. And typically, as I said already, typically you do that by means of 2x2 contingency tables. They are called confusion matrices at times. No, it's really your model. What does it tell your model to you if you compare the model with the reality, a yes or no reality, a yes or no model? 2x2. Yes, the model, yes, the reality, okay, true positive. Not the model, not the reality, okay, true negatives. Otherwise, you may have a false positive, you may have false negatives. This is the typical thing that you do and many people, many references here, yet. If I'm thinking about a regional system, a territorial system at regional scale, I'm thinking about a wide area. Let's assume with this cartoon that this is the area. And let's go and make, with a synthetic set of data, qualitatively speaking, I'm saying, let's consider time on the x-axis, let's consider warning level on the y-axis. Let's assume that we have a level that it's green, everything is fine. Then you may move to yellow, to orange, to red. So four levels, 1, 2, 3, and 4. Let's say it starts raining. Your warning model. Now I'm not concerned about why the warning model is doing what it's doing, but what's the effect? The warning models tells you that you go into yellow. Okay, time goes by, keeps raining, you are in the yellow alert, and then one landslide occurs. And then 3 landslides, 3 more landslides occur in different parts of your area, but you're still in a yellow warning level. Well, it keeps raining, the model tells you, you go to red. At the same time, you go to red and another landslide occurs. You stay in the red and 3 more landslides occur. So things are happening in this territory. It doesn't rain anymore, but that doesn't mean that the danger of the risk is over. So your model stays in the red warning level, new landslide. Then the model goes down to orange, stays in orange with a new final landslide occurring, and then at the end, you go back to green normal conditions. The question here is, was the performance of the model, the warning model that I just showed you, satisfactory? if we were live, we could discuss about it. Because I'm recording, I have to answer to my own question. Well, it depends. Not completely, but somehow, yes. See, I cannot really state something here, yes or no. It was satisfactory, yes, it was satisfactory, no. Because my judgment is based on what I look at. I may look at those and I may say, well, during those times, those landslides were indeed happening when the red alert, red warning level was issued. So, but at the same time, at the beginning, these landslides happened when yellow alert was issued. So I like it, but not too much. And then, you know, for a very long time, maybe a very long time, or some time after the last landslide, we were still in orange and nothing was happening. So I have to address these issues if I want to think whether this model had a satisfactory performance or not. In an attempt to objectively answer the question that I just posed to you, to myself, with this procedure that we called Adamup, we found a way of indeed putting things in order to objectively say whether you like or you don't like the performance of your system. And this procedure is essentially based at the center of everything. There is what we call a duration matrix, not a contingency matrix, but a duration matrix that is comparing, relatively speaking, the landslide events with the warning events in a matrix form, not 2 by 2, but n by m, depending on how many classes of landslide events you have, how many classes of warnings you have. 4. If it's 4, it's 4. So you start with defining what a warning event is, what a landslide event is, because a landslide event could be more than 5 landslides in my area, large landslide event. Or let's say more than 10, large landslide event. For Hong Kong, more than 15, large landslide event. But maybe it's like between 5 and 15. You can say moderate landslide event, or maybe you can say high, not very high. And then it's only 5, 4, 3, or maybe it's 0. So 0, for instance, no landslides, or something that I can call small landslide event, intermediate landslide event, large landslide event. It's me, the manager, not me, Michele Calvello now, but it's the manager of the system that decides what is a large, intermediate, small landslide event. You can even say that you don't want 4 classes, you want 2 classes, a yes or no, whatever. Then on the other side, you have the warnings. Warnings, as we saw, they are issued if it's more than one level with steps. You know, they may start with level 2, level 3, then go level 4. This case, they are level 3 all the way from the beginning to the end. And anyway, they have a duration from the beginning to the end of the warning event. The idea of the duration matrix, is to check the time when you have a large landslide event together, or a small landslide event, or an intermediate landslide event, together with what your warning model is producing. And if you check, you know, you have different intervals. In some cases, you like very much the fact that the system is telling you very high warning, maximum highest class of the landslide event. In some cases, you don't like very much that maximum warning and no landslides occurring. So you put all of those into a table and you call that the duration matrix. Are you done with your job? Not yet. Some final step is missing. You have to check whether what you have there in the table as numbers, times, is indeed something that is telling you that your system is working well, or is telling you that your system is performing not very well, could be improved. So you devise as a manager, what is for you a true negative. True negative for you is this, for instance. It could be that missed alerts, those two, correct alerts, those two, false alerts, those two. You can have a criterion that is a criterion for which this is the correct alerts, only these three, the green ones. Maybe you can have some errors, but not too bad, yellow, but then you have red errors or even purple errors. You define some assessment criteria for judging whether in parts or in subparts of your table things are going well or are not going well. And once you have those, you can go with some performance indicators and decide whether your system is performing well or not. Okay, I think that's enough. If you want to know more about a specific method, Adamup, besides an original paper, which one was that? Okay, an original paper that is this one, where indeed we were looking at landslides occurring in Rio de Janeiro. There are other papers addressing other areas of the world, Campania region, Norway, Piemonte, in Italy. And you can find more details, not only on the original proposition, but also on some modification and some extension, model modification, and some results if you're curious about it. Okay, I'm done. This is the end of the conversation, of the lecture, sorry. Concluding remarks. I want to put this sentence here, although it's sort of it's an eye-opener. Whether traditionally or technology-based, it's a sentence that was written more than 20 years ago. Early warning systems are only as good as their weakest link. And Maskely goes on in saying that they frequently fail for a number of reasons. Okay, that was 20 plus years ago. But anyway, it's important here to highlight the many components that we saw. They all work together, but there is not much redundancy in those components. If something is not working, the system is not working. Okay, you may have a perfect warning model, efficient, 100% true positives or true negatives, efficiency 100%. Yet, if people are not moving after you send them the alert, the system is not working. On the other way, you may have reactive people, but you send them wrong messages. They evacuate for no reasons for a number of times, then they get sick and they don't evacuate anymore. Anyway, it's the weakest links that run the show. It is a very much interdisciplinary endeavor, multidisciplinary, interdisciplinary, transdisciplinary. It's important to work across disciplines. I'm from civil engineering. Geotechnics is clearly at the center of it, together with engineering, geology, and the earth sciences in general. So the inner shell is this, but then you have other engineering, physics, statistics, economy, law, psychology, sociology, geography. Everything really is important for devising the systems that work. Finally, for those of you who are really interested in landslides early warning systems, I can tell you that in August 2020, so a little more than 1 year ago, a new international network was created. It's called LandAware, the International Network on Landslide Early Warning Systems. I have the honor to be the president of such a network for the time being. These are the people that founded, together with me, the network, and They are from all over the world, from UK, from Japan, from Italy, and there is also here from Italy. Then we have Switzerland. This is Norway. What is that? USA, from NASA, UK again. So it's a variety of people, and also I am actually the only professor among the lot. They are working at Met Office, BGS, NASA, and other operational systems in Japan and Norway, the operational national systems in Japan and Norway, the civil protection in Italy, Fausto Guzzetti. Okay, if you want to join, just go to the web. On the web, you can see that there are no active working groups. You can see that we already hosted a few initiatives. If you want to check on the material that is there, this initiative was a 24-hour-long initiative, and so you have a lot of recordings of that initiative with different topics. And anyway, if you want to join, it's very easy. And if you don't want to join, but just want to subscribe to the newsletter, it's also very easy. All that said, I am, yes, at the very end of my lecture. And the main reference for this lecture is an article that I published a few years ago called Early Warning Strategies to Cope with Landslide Risk. And you can get the article straight from the web, from my website, if you want. I thank you for your attention. And the lecture is over. Therefore, I guess, bye-bye. I have to close the recording at some point. How do I do it? Bye-bye.